Hello, Prashant.
Can we start?
Yeah, yeah. Yeah, yeah. Yeah,
Or
good morning, all of you. Just wait, wait. Good morning, all of you. So today is the last date, and he will be covering as per the content shared by his day 5. And wish you all a happy Duli Vandan, Holi and Duli Vandan. Thank you. Prashant, you can proceed with your agenda.
all right. Thank you, sir. All right. Happy Holi to all. I'll be sharing my screen. One second. Let's see. All right. It should be visible now. Um, so today is our
Yes,
last
yes.
lecture. Okay. All right. Thank you. So today is our last lecture, and today we are going to cover deep learning. Right? Um, from the beginning, we had an introduction. Then we had logistic and linear regression. Those are called linear models using supervised machine learning. Next, we did some more supervised machine learning algorithms like SVM, KNNs, decision trees. Then we did a couple of unsupervised learning algorithms yesterday, which were again k-means and principal component analysis. And today we are going to cover another paradigm of machine learning, which is called as deep learning. Um, so, what I'm trying to do today is I will try to give an overview of what deep learning is, not going too deep into the intricacies of training or the intricacies of the algorithms, but to give an intuitive view of how these algorithms work. So, deep learning is essentially neural networks, right? So anything that has any model that has a very high number of parameters within itself that need to be tuned and then trained are called so these type of algorithms are called deep learning algorithms. Usually, like they are anything, the study of neural networks is essentially deep learning. So, and the idea of a neural network, which are also in this context, in the context of machine learning, the technical term is artificial neural networks, because the actual neural networks that they have been inspired from are actually a part of our human brain, right? So the idea of a neural network really comes from the way in which neurons are connected in our own brain. um, the way signals are passed between two neurons within the brain, how one signal passes to the next neuron and then the next neuron, and how it combines for us to make some kind of a decision. Certain areas of our brain activate when we look at a certain visual, or we smell something, or any kind of a sense that we get. Triggers a certain part of the brain, and using that analogy and bringing it and scaling it down to a much smaller level, like our brain has like billions and billions of neurons in it. We scaled it down to, I mean, nowadays algorithms have crazy amount of parameters, but let's say maybe 20 years ago, 30 years ago, 40 years ago, when initial neural networks were made, those were like very simple models of our complex brain structures. So as you can see here in this diagram over here, this is how usually a neural network is represented. If you look anywhere, like, it has some inputs. So this is called the input layer, where you are giving whatever inputs you have, what you are, your data set inputs that you have. This is your output layer, which will predict something, which could either be a classification or it could be a regression, right? As we have learned in the past few days, we now know what classification is, what regression is. So these networks could be used as in for both types of data sets, for both types of problems. Uh, and the middle layers, these layers which are not a part of input and output, they're usually called as hidden layers, right? Now, it could have n number of hidden layers. It doesn't matter. A neural network, you can scale it up as much as you want. Now, each connection, as you can see here, is one each new. So this is called one neuron. Right? So this is called a neuron, and as you can see, in each layer, you will see that each neuron is connected to all the other neurons, right? So this type of a network is usually referred to as a fully connected network, where everything is connected to everything. So signal is passing. So you are giving the signal the liberty to pass from everywhere and fit to the data as better as possible. Right? So that's the idea. Now, usually, a neural network is treated as a black box, right? What is a black box? You don't really know what's going on within. So, in in a very simple neural network which has less number of parameters, it is you could kind of see how it works, and we will see that later in this lecture. We will see that how a very basic neural network configuration would work. But when it comes to a more complex network which has say millions of parameters in it, it is really difficult to figure out what exactly is causing the decision to be made. You know, what exactly is influencing neural networks ability to make that decision. For example, in case of large language models that we see nowadays, chat gpt, right? So gpt models are, they have like billions of parameters, and it is very difficult to figure out what part of the network or what parameter caused what decision making. It's very and that's why it is very difficult to controlling hallucinations of a large language model. Now, what hallucination means is that these models, these large language models, they're usually trained in such a way that the training regime is such that they will always keep on predicting something. So it won't say that the answer, right? It won't give you zero output. The models are trained in such a training pattern that they are always forced to give some kind of an output, and that output is usually wrong as well. So it could happen that just for the sake of giving some output, these GPT models, they give you some output, okay, and that might or might not be correct. Now, just diverging a little bit from our topic, I will give you an example which you can try with Chat GPT, right? So, if you ever query or you just ask Chat GPT to generate images, okay, of a clock, a simple wall clock or a wristwatch with time as say 10:30 p.m. or 10:30. The time should show 10:30. So it will always, most of the times, what it will do is it will generate an image of 10:10. So for example, the wall clock, you are asking it to generate an image like this, right? So between 10 and sorry between you are expecting something to look like this between 10 and 11 and then 6. So this is 10:30. But if you ask ChatGPT to generate an image, it will always generate something like this. It will be 10:10 always. And why is this the case? Because now that is what I have noticed until last week at least. Now I don't know if they updated the model and you're not able to see that, but I'm pretty sure this is still going to happen. Why is this happening? Why will this always, even if you ask for 10:30, it will always show 10:10? Why? Because, and this is classically, this is called as a hallucination. Why? Because if you go on the internet and you scrape all the data from all watch sites, right? Any website that is selling a watch, that is from Amazon or anywhere, watchmakers or watch sellers or watch companies, when they show an image of a watch, right? They always show 1010. Why? Because it resembles a smiley face. You know, the essentially uh, the angle that this makes represents a smiley face. So that's why most of the data that is available for clocks on the internet is always showing 1010, right? So what happens is ChatGPT is trained on millions of such images which always show 1010. So it doesn't really know what 1030 looks like. So uh, it's not able to give an output. But it won't ever tell you that I don't know what 1030 looks like. It will always tell you, okay, this is 1030, and it will give you this image. So that's a hallucination, and that's to figure out what exactly and what to tweak in parameters, and some small amount of them could be influencing this decision making, right? So you don't really know what is causing, and then it's a separate field of study where um, you are trying to figure out how these neural decision making processes work. But colloquially, neural networks usually are treated as, that's why they are called black boxes. They are often treated as black boxes because getting the right idea of how decision making is happening, especially in very large models, is very difficult. Okay, so coming back to a simple artificial.
So may I ask a question, sir?
Yeah, sure.
In the last slide, the structure of artificial neural network,
Uh-huh.
just you are seeing, sir, just this is a standard structure or it may be of different type? Because I always see the input of two circles and output of two circles are made.
Right.
So this is a standard structure.
No, so this is not this is an example. So yeah, but this type of a network is called a fully connected network. Now you could have multiple inputs over here, you could have multiple outputs. So this is not a standard structure. Like the number of parameters or the number of nodes in each layer can change. And also there are other architectures as well of neural networks, which I will discuss briefly by the end of this lecture, and we'll come to that. But yeah, this is not a standard structure. That's what I wanted to say.
Thank you.
Yeah. So all right, so let's move forward. So let's see how a basic artificial neural network works, right? So let's say you have data set that looks something like this. Okay, something you are basically doing some kind of a drug testing, and on x-axis you have the dosage of drug. Let's say it goes from, let's say the dosage goes from 0 to 1, where closer to 0 are smaller doses, closer to 1 are you're giving the patients heavier doses, and in the center you have medium doses of the drug. Okay, and that's what your simple data set. If the drug is effective, it will say yes on that particular patient, and if the drug is not effective, it will say no. Okay, so as you can see in this data set, we can already see that, okay, if the drug is given in medium amounts, it is effective on patients. But if it is given in smaller or very high amounts, it is not really that effective on our patients. So now what we want to do is we want to fit a curve to this data in such a way that we are able to predict based on the dosage that what kind of a drug this is, right? So essentially what we are trying to do is fit something like this, fit a curve that looks like this, and based on the dosage, then we will estimate. So for example, if the dosage comes at this point, right, someone is giving this dosage and I fit a curve that looks like this, I will plot this over here, and then I'll say, okay, so this dosage is, say this is 0.5, right? 0, 1 and 0.5. This is the midway line. So this dosage, the efficacy is below 0.5. So I would say that, okay, I would classify this as non-effective dosage. And if it goes somewhere here, then I would say it is an effective dosage. So let's keep the problem simple. Let's say we are trying to fit a curve to this data, right? Now, moving forward, we uh, we cannot really do this with a straight line, because as you see, we might want to uh, fit a curve. So that's why a regression model wouldn't really work in this case, or even logistic or a linear model wouldn't work in this case. You could argue for maybe something like an SVM, but again, you can use an SVM. You can project this to higher dimensions and then work it out. But then what if you have even more complex data sets? Like, consider you have this data set which you see here, where the pattern is changing like this, and the curve or the swiggle that you have to fit through the data, it varies in this way, right? So for this, what you want to do is, you want to the function that you're fitting to this data, the curve, that has to be very highly parameterized, so that it can essentially fit to the data, fit to complex changes or variances in the data, right? So that is why neural networks work very well to fit to these complex changes in the data, right? And so they work with complex distributions, and that's essentially the area where they perform very well. Now we come to the actual structure of the network, right? Uh, we Now I am not going to represent a neural network as you saw in the first slide, like this, right? I'm not going to show it like this. I'm going to represent it as a graph, so that it is much easier to understand what is going on, right? So let's say this is your input node, right? This is instead of circles, I am drawing squares, and basically these are those two nodes, hidden nodes, and this is the output node, and this is your input node, right? What we are going to do is, we are going to treat this network as a graph, and we are going to one by one do, and it is a simple network with one input, one output, and two hidden layer nodes, right? Just one hidden layer and two nodes. What we are going to do is, we are going to sequentially parse the whole network and try to see how a neural network makes its decisions. Now, for each of these nodes, right? For each of these nodes, they have some parameter associated with it. So, for example, for a line, it has, as we have been working with this for a long time now, line has two parameter, m and b, slope, intercept. So two parameters. But here, each node could have its own parameters. So each node could have its own weight. Each node could have its own bias, right? So each node could have its own. Usually, a bias is per layer. So this whole sorry, this whole layer could have a bias term, and each layer, each node would have its own weight, right? So you can think of it, if I have 1,000 such nodes, automatically I have 1,000 parameters that I have to tune on, plus the bias term. So so as you scale the new network, the number of parameters that you actually have to tune is going to increase. And that's where training this network efficiently is also very important. And that's where the technique of backpropagation, the backpropagation algorithm, is very useful, and it is used. And we will discuss this as well later on. So a neural network decision making, or the training loop, consists of two distinct processes. One is called as forward propagation, where what you're doing is, you are doing a forward pass through the network. So you give input data and get some output, and then during the training loop, you also do a backward propagation. So what you do is, once you do a forward propagation, you get some answer, you get some classification output or regression output, and you compare that output with the actual expected output that you had, and then you try to minimize the error. And how do you minimize the error? You basically start tweaking all these parameters, right? You will tweak these parameters and you will try to find optimal parameters by using gradient descent and by using back propagation. And we'll see that how that happens. But that's the whole training loop of a uh, neural network. So you have forward prop and then you go back prop. Forward back, keep on doing it until you optimize, you minimize your losses, and at the end you get a trained network. So now let's replace all these question marks. Yeah,
Sir,
yeah.
sir, you're saying that this is this. I mean to say that the neural network basically follows
Mhm.
the fitting of a curve, and it restricts the only two parameters, or it maybe increase the parameter.
It could increase. Yeah, it could have much more parameters than just two. So a line has two parameters,
Yeah,
but
of course, sir. Of
yeah.
course, a line has two parameters. Similarly, sir, I mean to say that these follows basically fitting of a curve, the theory
Mhm.
of. Yes, sir.
Yes, yes.
Okay.
The same concept, but the curve could go as complex as possible.
Yeah,
So
yeah,
you could, based on the number of parameters. So for example, if you have a very simple network in which you have like just let's say four parameters, right? So in that kind of a network will not be able to fit a curve that looks something like, let's say, this. Okay, because this is a much more complex curve, and in order to replicate this curve, we will
yeah,
need many more parameters to, like, you would, your the fitting function that you have, it would probably go like x raised to 6 plus 2 x raised to 5. Yeah, just
yeah,
giving an
yeah,
example, right?
yeah,
So that you need those many parameters to scale up to the complexities of data. So it really depends, but yeah, essentially you're fitting a curve only everywhere.
okay, okay, thank you.
Yeah, yeah. So uh, moving on, now what we'll do is we'll replace each value in these question marks that we had here. Let's say we have a fully trained network. Okay, now let's say this network is fully trained, and only we are doing inference now. Inference as in, I have a trained network, I have a test data point, and I want to see how it will. I have all optimal parameters already calculated. What I want to do is I want to um, see what the output is, or how the data, how is all the data being fitted, right? So let's say all these are the parameters. This is called the weight, this is the bias, this is the weight, this is the bias. Again, here I have some weight, and then at the output layer I'm summing up the weight, adding some more bias, and I'm getting some output. Okay, so now let's see how this works. And over here you can see a non-linear function, right? Now this is called as an activation function. So what we are trying to do is, you get an input, right? But now you want to fit a curve, right? To fit a curve to a data, you have to add some kind of a non-linearity to this data. You can't just scale the data up this way by adding by doing some linear scaling, like, by if essentially if you're multiplying a weight with whatever input I give here, it will just multiply by this, add by this, and that's it. I have to introduce some kind of a non-linearity to the way data is being fit, so that I can actually build a curve through this, right? So that's why we have something called as activation function at each of the nodes. And these activation functions help us to introduce non-linearity to our data, right? So what are activation functions? These are just like your, it could be anything. It could be your sigmoid function, right, that we learned a couple of days ago, 1 plus e raised to x. So this is your sigmoid. It could be a soft plus function. Again, it is commonly used for nonlinear activation. Uh, it's simply the log of 1 plus your exponential. So these these are commonly used nonlinear functions. Now let's move ahead and let's see how this will work. So let's
Sir,
assume, yes.
As you, sigmoid function e raised to the power x upon 1 plus e raised to the. Yes,
Yeah.
sir.
Yeah.
If we replace this particular exponential function can be general exponential function, that it is worked or not. Exponential function can be general exponential function, that it is worked or not. It will work or not.
So it depends how you define.
It will work or not.
So it depends how you define it. So if you replace it, so if you replace it with a regular exponential function, the trigger, I mean, happen is the question here. So if you are if you are uh, introducing a nonlinearity and the value of your parameter will scale, so in theory it will work, but the thing is, an exponential is not bound, right? It's not a bound function. What will happen is you are multiplying a value with, and you are exponentiating the function. So the the final value of this output is going to explode, and then optimizing that is going to be very difficult. So what you want to do is you want to stick to some bound functions.
Yeah.
Okay. Yeah. So so you can obviously tweak your e raised to x. You can, so there is something called as ReLU, which is rectified linear unit. So you can also introduce some kind of a cutoff within your function, that at what point do you want to cut it off, and based on that you can define these non. But I mean, exponential want to do that, but I mean, you could do it essentially.
Thank you.
Right. Okay. So moving forward,